Okay, so this is really the end of the bonding. Covalent bonds. Take a big breath because these are ones I think are most difficult. Okay, so in ionic bonding, something gives up an electron, the metal gives up the electron or electrons, and the nonmetal receives them. Positive, negative, opposites attract, they come together. These are formed by sharing, okay? So these are nonmetals. It's not a metal and a nonmetal, it's all nonmetals bonding together. Now if you think about it, on the periodic table, if you go back and look, we have this little small section in the upper right-hand corner of nonmetals, all right? So really there's not a whole lot that go into it, but there's still a lot of compounds that are made. So let's go through this real quick. Here it says nonmetals, right? They share one or more pairs. So at most we have up to 3 pairs. We either have 1, 2, or 3 pairs. Single, double, or triple bond. Okay. Oh, here we go, it says it. Now a lot of times in science and when people are talking about, they just use the word molecules all the time. I gotta go back. But really, molecules should only be used when we're talking about covalent bonds. All right, so here's a little bit example of what's going on. So these two things come together and they basically share the electrons back and forth. So let's say one type of atom needs 2 electrons and the other atom needs 2 electrons. Well, they could just share those back and forth, and so at any given time, each one would have 8 or an octet to be stable. All right. So when we do this, we actually count the electrons, the ones that are being shared for both atoms, and hopefully that makes sense here when I actually do the examples. They can be polar or non-polar. Okay. Sometimes we have non-polar things like, if you think of like a tug of war. You're both touching the rope, but one side's winning. And so the side that's, let's say, stronger has the electron more often. So what happens, it becomes slightly negative on that side, and the other side slightly positive. For what we're doing here, we'll just worry about drawing them, okay? And then polar means that they're just being shared equally, the paired up electrons. All right? There you go. Hydrogen and hydrogen share equally. So there's no side that has the positive. Water, on the other hand, oxygen has more pull on the electrons that are being shared, so therefore it's a little more negative, and the hydrogens are more positive. All right, so this is pretty much very similar to the last one. All right. But in this one, we're not going to have those brackets with the positive and negative ions because we don't have ions. So write that down, and then here we'll get into the drawing of them. The helpful hints are good. A lot of times I tell students, let's make them look symmetrical, and then it kind of ends up working out. I think it'll make more sense after we do some examples. No, let's go through a couple more slides. Let's go through a couple more slides here before we do this. So this is what we have here. So this will be an example of 1 shared pair. This would be 2 shared pairs, and then 3 shared pairs. Okay. I think a lot of times when I do the single pair, I'll have like x dot dot x, so they're away from each other this way. So if you think about these forming a line, 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 you have 1 line, 2 lines, 3 lines. Single, double, triple bonds. Diatomic or special ones, you have to memorize these. Okay. I mean, diatomic means 2, so these are just bonded with themselves. 2 oxygens bonding, 2 iodines bonding, 2 chlorines bonding. Now you can make up your own little saying to remember these. I think it's up here. This is a saying that some people use. I had students in another class make up other ones that I'm not going to say. Have no fear of brown ice cream. I did have pretty much a whole thing of ice cream last night. It's pretty good. There we go. So there they are, diatomic molecules. Hydrogen over here, okay? Even though it's over here on the left-hand side, and I said these are like metals here, hydrogen's that one exception. It's a non-metal. And then you have this little upside-down L. Those are your diatomics. And then allotropes. We already had allotropes, I thought, right? Molecules, same element. This happens with carbon a bit, okay? Carbon's a non-metal. If you ever hear of organic chemistry, it talks about carbon. But you have carbon that's maybe just arranged differently, but yet all carbon. Oil, coal, diamonds, that sort of thing. But it's all just carbon. Oh, there we are. There's what these structures look like. Here's your graphite. So all carbon just look different. They're bonded up a little bit differently. Okay. Oh, another one, yeah, oxygen, diatomic. O2 is what we breathe, it's what our lungs use. And then you have ozone, which is O3. Once again, all oxygens, but yet bonded a little bit differently. Phosphorus, another one. It's one I don't really quite remember ever. Should be it. Awesome. Blossom. Okey-doke. Let's go through the examples now, at least a few examples. Don't be surprised if you're struggling with these. It's perfectly normal. Okay, I think ionic makes a lot more sense, a little bit easier to follow. So first example, hydrogen. Hydrogen, H2. Now the difference between these and the other ones too, and the ionic compounds, if you notice in the ionic I said sodium and chlorine. In this one, it's actually going to give you the chemical formula, all right? And we just need to put it together. So first off, you're going to draw the electron dot diagram. Okay. Now it's weird to start out with an odd one, but hydrogen's kind of odd because it forms a single bond. I've also been known before to write them like this, okay? That they're sharing these together. So hydrogen's a special one. When it shares them, each one has two. If you recall, helium is a noble gas. It doesn't react. It only has two to fill its outer energy level. Well, this one has a full energy level with only two. It's the one special one. This is always a single bond. Do another one. It's a little hard to show with that one. This next one will be a little bit easier. So example 2. Let's do this other one first. O2. Okay. Oxygen. So oxygen is 6. 1, 2, 3, 4, 5, 6. And another one. 1, 2, 3, 4, 5, 6. Once you draw one, you know where they go. Just put them in really fast. Now, if I look at the total electrons, there are 12 total electrons, 6 plus 6. That's important, okay? Because when we do our bonding, we can have no more than 12 electrons being used. So question, this says 6. We need 8 for it to be stable. So how many electrons do we need? We need 2. If you notice, this one needs 2 to make 8. This one also needs 2 to make 8. So when we put them together, we basically have, let me see here. we have two bonds here that form, okay? So each one of these is sharing both of these. Now let's check to make sure we only use 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good, okay? Now we need to check each one to make sure it would have 8 at any given time. So put your hand over this. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 for this one. And then cover this one. 1, 2, 3, 4, 5, 6, 7, 8 for this one. Just touching the screen there. Okay. So 12 total used. 2 pairs are being shared. It's called a double bond. A double bond. Okay, kind of messy. We're going to do 2 more. Example 3, nitrogen 2. That's a 2. First off, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 electrons in each one, valence electrons. Total of 8. Total of 8. 5 plus 5, total of 10 total electrons. So we only have 10 to use. Now, this one has 5, this one has 5. So how many does each one need to get to 8? Each one needs 3. So let's try 3 bonds between the 2. So 1. Now, does that work? So they'd be sharing all these ones in the middle. We have a total of 10, so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10, so that fulfills one of the stipulations. Only use as much as you originally have. Secondly, make sure each one has 8. So 2, 3, 4, 5, 6, 7, 8. That one has 8, and obviously then, I keep touching the screen. I don't think I am though. And then this one, 1, 2, 3, 4, 5, 6, 7, 8, if we cover this one. So each one has 8, only 10 were used. This is called a triple bond. Because we had 3 pairs being shared. 3 shared pairs. Then the last one, hydrochloric acid, HCl. Hydrogen has 1. Chlorine has 7. 7 valence electrons. So let's just focus on the chlorine here. I'm going to tell you now, and I think I already said it, hydrogen always forms a single bond. That's it. It can't form a double bond. It only shares 1 electron. So here, chlorine only needs 1. So hydrogen, chlorine. 1, 2, 3, 4, 5, 6. So there's 6 from chlorine, and then one of them, 7, is being shared with hydrogen, and here's hydrogen that's being shared with chlorine. So I kind of missed this at the beginning. There's 8 total electrons here. Let's check over here. 2, 4, 6, 8. So that's good. Same number of electrons used. Now let's check chlorine to make sure it has 8. 1, 2, 4, 6, 8. Let's check hydrogen. 2. That's fine. It's perfect. Okay. Hydrogen's that special one. So there we go. It forms a 1 bond, or a single bond. All right. That's going to be it for now with this. All right. We showed the single, the double, and the triple bonds all by using diatomic. I'm going to put up another video that shows 4 more examples, but they're not going to be diatomic. They're going to have different things together, like just like this one. They weren't all the same.